Welcome to this presentation, where we will explain some of the weird and wonderful ways to use the Arista 7130 low latency FPGA based platforms. In today's session, we'll go over the 7130 series architecture, Metamux, and how to use it to create a networking hub functionality. We'll also discuss how we can leverage Metamux for aggregation and kill switch functionality. After this, I'll explain how the crosspoint helps create a more flexible switch than ever before, and we will finish off by discussing Metawatch and how we can make markets more deterministic by using Exchange App. Since the Arista 7130 series devices are not just any ordinary switch, I'll walk you through the basic building blocks of the Arista 7130 platforms, as well as some of the FPGA applications that Arista provides to get the most out of these platforms. I'll start explaining the architecture of the 7130 series platforms. Please note that this diagram walks you through an FPGA-based 7130 series platform. The entry-level Arista 7130 series Connect platforms share this architecture, but lack the FPGA and related components. The Xilinx UltraScale Plus VU7P-2 is used in Arista 7130L series devices, while the UltraScale Plus VU9P-3 is used in the Arista 7130LB series devices. The latter FPGA is more powerful, and we can run some more advanced applications such as Switch App on these platforms. All FPGA transceivers are connected through the crosspoint for maximum flexibility. While the FPGAs in the Arista 7130 series are fully user programmable, Arista provides standard applications as well. The examples that we will talk through today will only involve creative use of some standard applications. JTAG is an industry standard debug port for serial communication with the FPGA. Using the JTAG chain, we can load new software on the FPGA. Arista even provides a JTAG software package that provides a remote connection for development and debugging of FPGA application designs. The next highlighted part is the RAM. This particular part of the system is dedicated to the FPGA. It consists out of 4 modules of DDR4 memory running at 2400 MHz and can be used by the FPGA applications. For example, it's being used for debuffering in our own Metawatch and Exchange App applications. The control plane software, either MOS or EOS, managing the 7130 series, runs on an embedded x86 system. This system has its own CPU, RAM and flash memory. It also has an Ethernet, PCI Express, JTAG and timing connections. In addition to the Ethernet ports on the embedded system, Arista provides a dual port NIC for 10 gig Ethernet connectivity. These ports connect the fast path to the data path, as well as a high bandwidth connection to connect the control plane through the crosspoint. This can be used to run control protocols such as BGP and PIM on box when using the Metamux application. The Arista 7130L and LB series provide OCXO clock by default. This clock module provides a stable reference for our Metawatch and Exchange App applications and can be further enhanced using the Atomic Clock module or GPS. The Layer 1 crosspoint is the point where all other components are connected through. It can be used to connect front panel ports to each other, to an FPGA application port, or to the control plane through the embedded port or the 10 gig Ethernet interface. The Layer 1 crosspoint can be used to make one-to-one connections by interconnecting a sending and a receiving lane, but it can also be used to create one-to-many connections to mirror the same data out of multiple ports. Last but not least, the front panel facing ports, which consist out of either 32, 48 or 96 SFP+ interfaces that support either 1 or 10 gigabits per second, depending on the application that has been loaded on the FPGA. The 32 port variants also include an external PCI Express and SSD bay on the front panel. Let's change gears to the application side of things and see how we can make use of all of these components packed together. We'll start with Metamux, which might be weird if you're into normal networking, but also wonderful if you've already deployed it to optimize your trading environment. Metamux allows us to use the FPGA to take packets that come in from multiple transceivers and aggregate them to exit through a single output. This output can then be sent out on a single port or to multiple ports using that layer 1 crosspoint. The typical use for this application is for trading firms to share a trading venue handoff between multiple latency sensitive machines. In many cases, those machines themselves would use FPGAs to reduce the application latency, so the latency of a traditional switch would have a relatively large impact on the total system performance. Using Metamux, we can aggregate data from multiple machines into a single link using an average latency of 39 nanoseconds. This is the average latency, not the minimum, and was measured port to port on the front panel of the device, so it also already includes the latency of the SFPs. Looking at our diagram, the orange lines represent the path from the application machines to the trading venue, essentially the trades that are being sent into the venue. A single Metamux instance is able to aggregate up to 48 ports into a single link. The path from the trading venue to the application servers is shown in blue. This path is directly connected through the crosspoint and therefore pure layer 1. This means that it has a latency of 5 nanoseconds. This means that the round trip time of the whole system is now down to 44 nanoseconds, which is around 9 meters of fiber span. While this low latency is of course a great thing, there are some other weird things to take into account when you are replacing a traditional switch by a 7130 series device running Metamux. The first thing is that, because there is no manipulation of any headers, just aggregation, the MAC address of all of the application servers should be the same. The second thing is that the 7130 running Metamux is not layer 2 nor layer 3 aware. So for the system to set up a BGP and or PIM session to the trading venue, the same logic should be applied. This means that the NIC of the control plane, which can run these sessions, should have the same MAC address as the trading servers and also should be connected to the same Metamux instance through the crosspoint. This diagram shows that it is possible to carve the FPGA into multiple muxes using profiles as well. This is very convenient if a customer has a slightly lower density site with multiple uplink links to trading venues. As you can see, Metamux is quite flexible in terms of profiles. These profiles have a wide range of mux setups, ranging from 1 mux with 48 ports all the way down to 6 muxes of 8 ports. We'll show some examples of how those ports can be put to good use in the next few slides. One of the weird and wonderful things that we have been seeing built using this hardware is the creation of high-speed networking hubs. This is quite a niche use, but we thought it would be fun to revisit 1990 with modern day speeds. There are several ways to create a networking hub, one being larger size, while the other is being more flexible. The first scenario we want to explore is using a single Metamux instance. Because every bit is being replicated to all of the ports, the maximum bisection bandwidth of this mux is 10 gigabits per second. As you can see in this diagram, all of the application servers are connected through a single Metamux instance through the crosspoint. This is shown in orange. This data is then being sent back out from a Metamux application port back to the crosspoint. The next step is connecting the data that's being sent back out using the one-to-many functionality of the crosspoint. By making connections from the Metamux output port to all of the transmitting lanes of the front panel ports, we create a functional hub with a 10 gigabits per second data rate. This brings us to the next networking hub scenario. This one is slightly more complicated as it leverages 6 smaller hubs. Each of these hubs has a maximum of 10 gigabits per second bisection bandwidth, and we can choose which front panel ports are being connected to which hub or hubs. Each hub has a maximum of 8 input ports. In this diagram we show how we connect all of the input from application server 1 to all of the 6 hubs. We can then replicate the output of MUX1 to a single front panel port, or we can opt to connect it to multiple front panel ports. In this example, we will connect MUX1 just to front panel port 1. We can be very flexible in this, as shown here. We connect the input from application server 2 just to hubs 3 and 2. There are also options to connect the output of a single MUX into multiple transmitting lanes of front panel ports. In our diagram, we connect MUX2 to the front panel ports 2 and 3. The last diagram shows connections in a setup where a single MUX instance is assigned to each front panel port. This gives us the greatest control in which data goes in and comes out of what port, but as you can see, it has quite a few connections. This brings us to the next creative use of Metamux that we've seen in the field. Sometimes a trading application is capable of handling multiple exchange feeds to ensure that it acts with the least amount of latency. To assist with such logic, multiple Metamux instances can be enabled on a single 7130 series device. One of those muxing instances can then be used to aggregate the exchange's feeds into a single data stream, while the others can be used to take care of the return paths of the traffic. Let's walk through this using this diagram. The first step is to connect both trading venues' feeds into a single MUX. The second step connects the output of the MUX to the transmit lanes of the front panel ports connecting to the application servers. In the next step, we can choose to which MUXes we connect each application server. In this example, application server 1 sends its trades into MUX 2 and 3 respectively. By leveraging this logic, it's possible to choose to which exchange or exchanges the trades from a certain application server will be sent. The last part of this diagram shows how we connect the output ports from the MUXes, where the trades get aggregated, to send them back to the exchanges. Metamux also offers the storm kill feature to protect MUXes from badly behaving inputs. To this end, we can disable certain ports when either unicast or multicast traffic exceeds a certain threshold. In this example, an event occurs in trading venue A that causes a large amount of data to be sent into the system. The traffic flows through the crosspoint and enters the muxing instance. Then the muxing instance detects the burst of traffic and shuts down the respective input port to limit impact to other devices which are attached to the same muxing instance. The same feature applied to other muxing instances can also protect return traffic from badly behaving application servers. Switch app brings layers 2 and higher to the 7130 LB series. The crosspoint gives some even greater flexibility than was present in any switch before. Switch app is used to bring layer 2 and in the near future also layer 3 functionality to the Arista 7130 LB series devices. The FPGA is programmed to perform logic that is typically handled by switching ASICs, but with significantly lower latency. By enabling the switch app application on the FPGA in the 7130 LB series device, the device will effectively transform into a switch. The key difference is that this device still has the crosspoint capabilities, which allow for some weird and wonderful possibilities. The default configuration has got the front panel ports directly connected to the switch ports on the FPGA. This means that out of the box, a 7130 LB series device running switch app will function similarly to a normal switch. However, because the device also has a crosspoint, we can still apply the one-to-many logic. This way, if switching logic would send out packets to a certain port because it knows the destination MAC address is reachable behind that port, we can still send out copies of the same packet to other ports as well. As shown in the diagram, this is done by configuring the source interface switch 11 on multiple front panel Ethernet interfaces. Another use of switch app combined with the crosspoint is when a packet needs to be switched and mirrored at the same time. By simply using the crosspoint to send out traffic that comes in on Ethernet 1 on other Ethernet ports, we can have a normal crosspoint logic apply. This results in the same data packet being sent to the switch app for layer 2 processing, as well as being sent out to other front panel ports using its ultra low latency data path of 5 nanoseconds only. This brings us to the last subject for today. We're briefly going over Metawatch and discuss an application Exchange App. Exchange App is an application which has the potential to change the way that determinism works in exchanges. Metawatch is an application which is used for tap aggregation environments where timestamping, accuracy or large buffers are important. The blue circles in this diagram are the endpoints that could be tapped. Those circles could be anything: application servers, WAN links, switches, etc. In the bottom of the diagram we also see packet capture tools. Those could be any tool which ingests raw packet data. Once again, the blue and orange lines are the transmit and receive paths between a single port. Last but not least, the vertical lines are taps created using the one-to-many functionality within the crosspoint. Using Metawatch, we can tap and aggregate data without disturbing the data that is being sent between those devices. We do, however, regenerate the signal because the 7130 is an active device. That's why we call this regenerative tapping, with a latency penalty of just 5 nanoseconds. Metawatch can tap up to 4 groups of 12 ports in parallel, which will be sent out on 4 different output ports. The aggregated ports can then be interconnected to front panel ports through the crosspoint to feed into an arbitrary number of packet capture tools. Each group of 12 tap ports has a dedicated 8 GB of DDR4 buffer. This makes for 32 GB of total buffering capacity. The aggregate bandwidth of the DRAM is over 480 gigabits per second. This means that we can buffer traffic bursts of 48 times 10 gigabits at line rate. When Metawatch is used for timestamping, it adds a timestamp in the Metawatch Ethernet trailer format. This format includes metrics like the port ID, device ID, bit flags to check whether the FCS is valid, seconds or nanoseconds since the epoch. Optional extensions also include picosecond resolution timestamping and sequence numbers. The Metamux Ethernet trailer format dissector is also being supported in Wireshark since version 2.6 and up. We're now switching gears to Exchange App. Exchange App works in a similar way as Metawatch, but instead of simply forwarding and mirroring packets without doing anything to the original packet, we timestamp the packet and then add the Metamux Ethernet trailer to it. This is done by having every packet that comes in to the network pass through the FPGA, then timestamping the packet and returning it through the same application port. The net result of this is that every packet that comes into the Exchange network now has a picosecond resolution timestamp attached to it. The Exchange matching engine can now execute trades based on the arrival time on the edge of the network, instead of having to pass through a network that could have slight levels of indeterminism. I'd like to thank you for attending this session about some of the weird and wonderful things we can do with Arista 7130 series devices, and we hope to see you again in the next session. Thank you.